Hello friends, greetings from Professor Mayank I. Vyas. I am an Associate Professor, Government Engineering College, Modasa. Dear friends, we are learning heat engine. We have started this chapter and we have gone through a considerable topics. Let us see what we have learned. Heat engine, we have seen what is heat engine, classification of a heat engine. Then we have seen the cycle, what is cycle, the different cycle. First we studied the Carnot cycle, which is ideal cycle. We have seen the Carnot gas cycle and Carnot vapor cycle. We have also seen the limitations of the Carnot engine. Based on that, practical engine concept came, where the engine works on the different cycle other than the Carnot. It has some low efficiency but produce some useful work. In this context, we have seen the Rankine cycle, where the vapor is used, vapor of H2O is used, the main component of Rankine cycle, boiler, turbine, condenser and pump. We have derived the efficiency of the Rankine cycle. We have also solved a small exercise based on Rankine cycle. Then we have also studied, we have learned the Otto cycle, where the two constant processes are there. Today we are going to take small exercise on this Otto cycle. Then we will see the diesel cycle and the exercise on diesel cycle. Let us have one exercise based on Otto cycle. In an air standard Otto cycle, the minimum temperatures are 1550 degrees centigrade, 1550 degrees centigrade and 25 degrees centigrade. The heat supplied per kg of air is 900 kilojoule. Determine the compression ratio, the cycle efficiency and the ratio of maximum to minimum pressure in the cycle. Take gamma is equal to 1.4 and specific heat at a constant volume CV is 0.718 kilojoule per kg Kelvin. Let us solve. It is the problem of Otto cycle. Otto cycle. What is given? It is given the maximum temperature, that is T3 is 1550 degrees centigrade. Minimum temperature that is 25 degrees centigrade. Let us recall the figure of Otto cycle. Let us see the figure of Otto cycle. This is your PV diagram, right? These are the point 1, 2, 3 and 4. This is the compression from 1 to 2. So this is the minimum temperature. 2 to 3, heat supplied or heat addition takes place. 3 to 4, expansion, and 4 to 1, heat rejection. Right. So, if we refer this figure, maximum temperature is here, 1550 degrees centigrade, 1550 degrees T3. Minimum temperature is here, that is 25 degrees centigrade. So this is minimum temperature T1. Convert this to into Kelvin, 183 Kelvin, and this is 298 Kelvin. What additional is given? Heat supplied is given QS, that is equal to 900 kilojoule per kg is given. You have to determine what you have to determine. Determine the compression ratio. Compression ratio is equal to R. Cycle efficiency eta, and the maximum to minimum pressure ratio. Maximum to minimum pressure ratio. What is maximum pressure? Maximum pressure is here, P3. What is minimum pressure? Minimum pressure is here, P1. So minimum to maximum, P3 upon P1. These three we are interested. So what we have a heat supplied with us. We have heat supplied is equal to QS is equal to CV into T3 minus T2. We have CV T3 minus T2, that is equal to 900 to 0718, that is the value of CV, that is already given. T3 with us 1823, 1823 minus T2. So if you solve this, simplify by solving it, you will get T2 is equal to 569.52 Kelvin. This you will get. So compression ratio is equal to R is equal to V1 upon V2 is equal to T2 upon T1 raised to 1 upon gamma minus 1. R is equal to V1 upon V2 is equal to T2 upon T1 raised to 1 upon gamma minus 1. Put the values is equal to 569.52 upon T1 is equal to 298 raised to 1.4 minus 1. T2 569.52, T1 298. Gamma, it is given 1.4. This gives you 5.04. So, your first answer R, compression ratio is 5.04. This is your first answer. Next we are interested to find out the efficiency. We are interested to find out the efficiency of the cycle. Let us see that here efficiency of the cycle efficiency is equal to eta is equal to 1 minus 1 upon R raised to gamma minus 1. So, is equal to 1 minus 1 upon, what is R? R we have find out, it is 5.04 raised to gamma 1.4 minus 1. Solving this, you will get 47.65% eta. Cycle efficiency is 47.65. Efficiency is your answer 2. Then you have to find out the maximum to minimum pressure ratio. You have to find out maximum to minimum pressure ratio, that is P3 upon P1, P3 upon P1. So we are interested pressure ratio P3 upon P1. So, how will you get it? P3 upon P1. Let us go to find out this. P2 is equal to V1 upon V2 raised to gamma. So, this is equal to 5.04 is to 1.4 into P1 is equal to 9.63 P1. You will get the relation P2 is equal to 9.63 P1. Now, P3 upon P1 is equal to T3 upon T2 is equal to 1823 upon 569.52, because it is already with you. The T3 is 1823 and T2 is 569.52. So 1823 upon 569.52 is equal to 3.2. So maximum pressure upon minimum pressure is equal to P3 upon P1 is equal to P3 upon P2 into P2 upon P1. Hence, P3, hence you can say that it is 3.2 multiplied by 9.63, because P2 upon P1 we have a 9.63, P3 upon P2, this is your P3 upon P2. P3 upon P2 is equal to T3 upon T2 is equal to 1823 upon 569.52 is equal to 3.2. So P3 upon P2, this value is 3.2. P2 upon P1 we have already derived, it is from earlier that P2 is equal to 9.63 P1. So P2 upon P1 is equal to 9.63. This value we put here 9.63. So this comes 30.83. So pressure ratio maximum to minimum is equal to 30.83 is your answer 3. Is your answer 3. So friends, once again I am repeating, it is the Otto cycle. This is the cycle diagram on PV plane. Maximum temperature is given 1550 degrees centigrade, that is 1823 Kelvin, that is at this point. Minimum temperature T1 25 degrees centigrade, that is 298 Kelvin, that is at this point. Heat supplied here is given 900 kilojoule per kg. You have to find out the compression ratio R, cycle efficiency tau, and maximum to minimum pressure ratio P3 upon P1 is how much. Heat supplied is equal to QS CV T3 minus T2. Based on this you will get T2 569.52 Kelvin. We have equations that compression ratio R is equal to V1 upon V2 is equal to T2 upon T1 1 raised to gamma minus 1. Put the values, you will get R is equal to 5.04 Kelvin. Cycle efficiency tau is equal to 1 minus 1 upon R raised to gamma minus 1 is equal to 1 minus 1 upon 5.04. You put this, you will get the cycle efficiency, and the pressure ratio P3 upon P1 you will get. First you get in the form of P2 upon P1 9.63. Second time you get P3 upon P2 3.2. So P3 upon P2 into P2 upon P1 gives you this P3 upon P2 30.83. Let us have one more exercise. based on the same Otto cycle. An engine is operating on the ideal Otto cycle having a bore of the cylinder 15 cm and length of the stroke 14 cm. If the clearance volume is 290 cm3, find out the air standard efficiency of the cycle. I am repeating the data. Try to understand. An engine is operating on the ideal Otto cycle. It is Otto cycle. Having the bore of the cylinder 15 cm, the bore, so that is the diameter of cylinder, that is equal to D, that is equal to 15 cm. Length of the stroke, that is stroke length, is equal to L, is equal to 14 cm. If the clearance volume is given, clearance volume is equal to VC. Clearance volume is given VC, that is equal to 290 centimeter cube. 290 centimeter cube. Find out the efficiency of the cycle. Find out the efficiency of the cycle. You are knowing very well that Vs is equal to the stroke volume or swept volume is equal to pi by 4 into d square into L. Put the values. Pi by 4 d square is already with you, 15 square into L 14, you will get 2474.0, that is the volume is centimeter cube. 2474.00 centimeter cube volume. So the compression ratio is equal to R is equal to V1 upon V2 is equal to Vs upon Vc upon Vc. This you have already learned. Compression ratio R is equal to V1 upon V2. So initial volume to the volume after the compression process. What is V1? It is the volume at the beginning of the cycle. What is V2? It is the after process 1 to where compression action takes place. At the end of the compression, whatever the volume is there, V2. V1 we have already seen during the theory part, Vs plus Vc, that is swept volume plus clearance volume upon Vc. So this is equal to 2474 plus 290 Vc upon 290 clearance volume. This comes R is equal to 9.53. R is equal to 9.53. see, efficiency is equal to 1 minus 1 upon r raised to gamma minus 1, r raised to gamma minus 1, so is equal to 1 minus 1 upon 9.53 raised to 1.4 minus 1. Solving this, you will get 59.41% eta, 59.41% efficiency. So friends, we have seen two small exercises based on the Otto cycle theory. We learned the Otto cycle theory. We understood what is the Otto cycle by solving the two exercises. Now we are moving further to our next cycle, that is diesel cycle. Diesel cycle. Diesel cycle is basically the constant pressure cycle. It is basically the constant pressure cycle. At constant pressure, the heat addition takes place instead of that constant volume which we have shown in Otto cycle. Diesel cycle basically invented by Rudolf Diesel in a way back 19th century, in the later part of the 19th century, and it is used in the diesel engine. Let us see what is in diesel cycle. Diesel cycle. What is in diesel cycle? In a diesel cycle, heat addition takes place in constant pressure during the constant pressure process. It is Rudolf Diesel somewhere in 1897 invented this cycle. What is in this cycle? We'll see. The cycle on two plane PV diagram and T temperature entropy diagram. The process starts at point 1, process start point 1 to 2 process is isentropic compression. Let us see the process 1 to isentropic compression. As a result, pressure increases, temperature also increases. That you can show here. Point 1, point 2. Heat addition takes place during the process 2-3, here heat supplied QS, that process is this. This is your point 3. This is point 3. Heat in. Addition of heat takes place. At constant pressure, pressure remains constant, P2. Is equal to P3. Then process 3-4 is isentropic expansion. Process 3-4, isentropic expansion. Process 3-4, isentropic expansion. Let us see here. Process 2-3, heat addition at constant pressure. Process 3-4, isentropic expansion of air takes place. 3-4. As a result, pressure decreases. Pressure decreases, also temperature decreases. And then the process 4-1 back. Process 4-1. So this is the diesel cycle. Heat rejection takes place in process 4-1. Heat is rejected. Heat out. Right. So process 4-1 is heat rejection is carried out. Heat rejection is carried out at a constant volume. At constant volume, that is here. You can see the volume remains constant. V1 is equal to V4. So we have seen the cycle, diesel cycle, where you can see the process 1-2 is the isentropic compression process, 2-3 heat addition at a constant pressure, 3-4 isentropic expansion, 4-1 again heat rejection. The same cycle on temperature entropy diagram, 1-2, 2-3, 3-4 and 4-1. See, slide. See, that you can see process 1-2 isentropic compression of air, pressure and temperature of air increases. That is shown with the blue line. Process 2-3 heat addition takes place at a constant pressure. P2 is equal to P3. Process 3-4 isentropic expansion of air takes place. Pressure decreases. Here the work is developed during the process. And process 4-1 heat rejection takes place at constant volume. We are interested to carry out analysis and to find out the formula for the efficiency. Efficiency of the cycle. First, net work done is equal to heat supplied minus heat rejected. So, it is QS minus QR. This is equal to heat supplied at a constant pressure at Cp. So, Cp we are taking T3 minus T2 minus heat rejection is at constant volume. So, MCV T4 minus T1, right? So, efficiency is equal to eta is equal to net work done upon heat supplied. This is equal to QS minus QR upon heat supplied QS is equal to, put this M into Cp T3 minus T2 minus M Cv T4 minus T1 upon M into Cp T3 minus T2. Simplified this equation, you will get eta is equal to 1 minus T4 minus T1 upon gamma T3 minus T2, because we had Cp upon Cv is equal to gamma. This we have with us, right? Let us say this is the net work done. This your equation A. This is your equation A. We have compression ratio is equal to R is equal to V1 upon V2 with us. Let us define the cutoff ratio. Cutoff ratio is equal to RC is equal to V3 upon V2, and expansion ratio is equal to V4 upon V3 is equal to V4 by V2 upon V3 by V2. Now here we have in our cycle V4 is equal to V1, V4 is equal to V1. So you can take V1 upon V2 upon V3 by V2. This is equal to R upon RC. Expansion ratio is equal to R upon RC. Compression ratio upon cutoff ratio. This is very important. So for process 1, 2, we can write T2 upon T1 is equal to V1 upon V2 whole raised to gamma minus 1 is equal to R raised to gamma minus 1. Hence, T2 is equal to T1 into R raised to gamma minus 1. Let us say this equation is B. We will use this in the later on. For process 2, 3, we have P2 V2 upon T2 is equal to P3 V3 upon T3. But P2 is equal to P3. So you can write T3 is equal to T2 into V3 by V2. Substitute the value of this T2, the value of T2 from the equation this B, equation B, T2 is equal to T1 R raised to gamma minus 1. You can T3 is equal to T1 into R raised to gamma minus 1 into V3 upon V2 is what? What is V1 of V3 upon V2? V3 upon V2 is nothing but the cutoff ratio RC. It is nothing but the cutoff ratio RC. So T3 into RC. Let us say this equation is C. This equation is C. For process 3, 4, T4 upon T3 is equal to V3 upon V4 is to gamma minus 1. But we have V3, V4 by V3 is equal to R upon RC. So T4 is this, T4 upon T3 is equal to V3 upon V4 gamma minus 1. V3 upon V4 is what? RC gamma minus 1 upon R gamma minus 1. We have opened the bracket. Put the gamma minus 1 on numerator and gamma minus 1 denominator. Right. So, here you can write T4 is equal to you can take T4 on back side. You can write T4 is equal to T3 into compression ratio RC gamma minus 1, cutoff ratio gamma minus 1, compression ratio R raised to gamma minus 1. Now you have to take this value of T3 from the equation C. This equation T3 value is this. Put this value or substitute the value of T3 in our this equation. This is equal to T3 is T1 into R gamma minus 1, right, into RC. T1 into R gamma minus 1 into RC plus this into this. This term, what is that? RC raised to gamma minus 1 upon R raised to gamma minus 1. By simplifying, you will have T4 is equal to RC cutoff ratio raised to gamma into T1. RC raised to gamma multiply by T1. This. Let us say this equations, the value of T4, that is equation D. So you have to put now the values of T2, T3 and T4 in our equation which we have used, this A, equation A, that is efficiency is equal to 1 minus T4 minus T1 upon gamma T3 minus T2. This is equation A. You have to put the values of T2, T3 and T4 from the different equation which we have derived. T2 we have derived. T2 is equal to T1 R raised to gamma minus 1. T3 is equal to T1 R raised to gamma minus 1 into RC. And T4 is equal to RC raised to gamma into T1. Substituting this value in the equation, eta is equal to 1 minus T4 minus T1 upon gamma T3 into gamma T3 minus T2. Put the values of T2, T3 and T4 and simplify. you will get 1 minus 1 upon r raised to gamma minus 1 into 1 minus 1 upon r raised to gamma minus 1 into rc raised to gamma minus 1 upon gamma into rc minus 1. This is what the equation of the efficiency for the diesel cycle. This is the equation of efficiency for diesel cycle. Once again, what is the equation? Cycle efficiency is equal to 1 minus 1 upon r raised to gamma minus 1 into rc raised to gamma minus 1 upon gamma into rc minus 1. This is the equations. It is clear from these equations that efficiency depends on the compression ratio R, the ratio of specific heat gamma, and the cutoff ratio RC. Efficiency can be increased if the R, if we increase the R, efficiency can be increased. If cutoff ratio decreases, efficiency can be increased, and also go with the gas which has the large gas which has large value of gamma. You can increase the efficiency of the cycle by 3 ways. Either you take the R at a higher level, RC lower down, and the gamma value is the R. The efficiency of diesel cycle, is always less than the efficiency of Otto cycle. Efficiency of the diesel cycle is always less than the efficiency of the diesel cycle for same compression ratio. So friends, we have seen the diesel cycle, the working of the diesel cycle, the process or the cycle analysis on PV diagram and temperature entropy diagrams, and then we have find out for the cycle efficiency and how the cycle efficiency is depend on the various parameters. Friends, thus we have completed the diesel cycle. A small exercise we are interested to take on the diesel cycle that we will see next time. Till then, a very best wishes from all of us here, wishes and prayer for your all-round success and happiness in this college life and the later on. A very thank you very much.